Well, it's warmer today, and we're going to do class L. Class L is the Dirac equation, and one of my most favorite classes. Brilliant work of Dirac to come up with this equation that's named after him. And it describes the electron in the relativistic and quantum mechanical realm. That's the realm of the fast and the small. And we're going to see that when we have a marriage of relativity and the quantum world to get relativistic quantum mechanics, that in this case, with the Dirac equation that describes the electron, we give birth to two children, and the children are the spin of the electron comes out naturally, and antimatter, a bonus that antimatter exists. That'll lead to the discovery in a few years from Dirac to the positron. Dirac is doing his work in 1928, not long after the Schrodinger equation in quantum mechanics in 1925, and Heisenberg and all that. And then they discover that there's a particle that has the same mass as the electron, the same m, and that's important. You're going to find that today, that there's going to be four solutions coming out of the Dirac equation, like four particle states, and that antimatter, the anti-electron discovered in 1932, has a positive charge instead of a negative charge. Now, there are some problems with the Dirac equation. It's not perfect. It'll predict some negative energy, and that's going to be a problem, and that later is dealt with in quantum field theory. So just keep focused on those, look forward for those two outcomes of the Dirac equation: the spin of the electron and antimatter. Let's go. Chapter L, the Dirac equation. L1, review of spin and the Pauli equation. When we looked at spin, we worked within the framework of matrices and groups. It never ceases to fascinate me that mathematicians develop beautiful architecture in mathematics often before, physicists use them, these things. And here is Sophus Lee, 1843 to 1899. And he worked with groups and Lie groups. And let's look at these a little bit because we're within his family. Now, the group, a general group you can make, called the GL, general linear, n by n matrices over the complex field, so complex numbers. They call it linear because a matrix operator, when you have an A matrix and you operate on a, say, two vectors, say these are column vectors like this, that you can pull out, like this is like a number like 2 or 3, this is a scalar, a number, you just pull that out, and you can have the matrix multiply this column matrix and then pull out the beta, and A works on this one. So you can think of this A as like an A11, an A12, an A21, and A22, and this U could be here like a C1 and a C2, for example. And this is a linear property where you can operate on the first one and then plus operate on the second one. So here's a little map I found on the internet. And this here is the general linear groups, n by n, complex. And then if you drop down the reals, you can come down here. Or you can go to special linear, and then that would be SL and C. Or you could go unitary and special, or just unitary. Remember, the unitary, the matrix, the dagger is the inverse. And for special, you want the determinant of A to be equal to 1. Then we talked about orthogonal cases. In fact, down in here, special orthogonal, if you have 2 here, 2 by 2 at real numbers, this would be our rotation matrix. And orthogonal means if you take this, like multiply these two and multiply those two and add them, you get 0. So that's cool. So this is like kind of a nice map of matrices and groups. Very nice. And these are Lie algebras named after Sophus Lie. See, these are the algebras. We found these relationships with the orbital angular momentum and the Pauli matrices. And then when we put in the h bar and divide it by 2, we were able to find the second one, make it look like the first one, where then this becomes S sub j, and this is S sub k, this is S sub L. So this is just a little moment of review of what we did earlier, and to talk about the classification of the matrices here, and give some attention here in respect to Sophus Lie, honor Sophus Lie here, as these are Lie algebras and Lie groups. So then the Schrodinger equation that we did, if we write that down, then let's do it in one dimension. We would have, say, the derivative with respect to x, second derivative, plus v psi is I h bar d psi dt. And if you look at the time independent case where the v, which could in general be a function of xn time, if it's just a function of x, then we looked at the simplification where the wave function is equal to some function of x, and then here we have the e to the minus I omega t. And when you plug that in, we did this. This is going to pull down a minus I omega. You get h bar omega, which is your energy on the right-hand side. And then you'll get an e to the minus I omega t that will be everywhere, which divides out. So remembering the energy, you could actually write this if you'd like. You could write this as e to the minus. You could put in what the omega is, e over h bar. So you could put e t over h bar like that if you want. So then this equation the time independent case would be, here we just have now one variable, the x. But just looking at this equation for a second, this equation's no good for relativity because look, x squared and t, they're not on an equal footing. And in relativity, you're going to want x and a ct to appear like this in different places. And if x is squared, c squared, t squared, you're going to want that also. So that's problematic there. If we proceed, though, to the Pauli equation, then we would have, and we go here, we'll go 3 dimensions here. Then we have a spinner, and the potential can not only be a function of, say, x, y, z, and even t, it could be replaced by a matrix. So this would be the time. Let's go ahead and make this one time independent. And that means in this case, v is only a function of x, y, and z, like no time dependence. Then to write this out as a full matrix equation, it's understood here that you would have the identity matrix. And let's go drop down to 1 dimension here. So we'll have the second derivative like there. And then for this v, we have a matrix. And the eigenvalue problem, where you have the eigenvalue, the energy, and the eigenvector would be what you're solving for. So that would be the Pauli equation. So that's Pauli equation. And this one up here, Schrodinger equation. But see, this problem here with not being in agreement with relativity, remember our wave equation where we had here like the second derivative of a wave with respect to x. This is good old-fashioned classical waves, is equal to 1 over light waves. Remember this equation? See, that's in agreement with relativity. You have the x squared and you have the c squared, t squared here. And remember how to remember this, if that's meters squared, to get meters squared, you need to have distance is velocity times time. So that, see, this is good. This is good. This is not relativistic. And we know that, so let's look at here a search, and the Klein-Gordon equation will be the title for this next section. So when we look at our nice little box diagram where we have the speed, and we're going fast here, we're going slow. This is relativity. You could say relativistic mechanics. And then here, F equals ma, this is classical mechanics. This is the world of the large, and then this is the small. And here I'll put the de Broglie relation, but you could use the Schrodinger equation in there. And then this is Dirac, and I should add others because work still goes on in this area. Dirac didn't give the final word. And modern physics consists of relativity and quantum mechanics. And this would be relativistic quantum mechanics, and that's what we're looking at today. So what's called modern physics in the curriculum would be special relativity, relativistic mechanics, special relativity, and quantum mechanics. So these two. Now, when you go into this realm, we're going to make a marriage of these two. And when these are married, I'm going to show you today, you get 2 children. You get spin of the electron, you get the spin of the electron, and you get antimatter. This is the big, deep philosophy or philosophical part of today's class in theoretical physics. Just remember here that this is smaller on the size when you go this way. And remember that the speed of light appears in relativity when you compare the speed, you're comparing with the speed of light. If you're a lot less than the speed of light, you're then down in here. And the magic constant here is h, the Planck constant. And remember the Planck constant we showed in the last class, this has units joule seconds. So if you were to find a characteristic energy of your system in joules and multiply by a characteristic time, some say the time of the interaction, then for to be really small, you know, this is of the order of like 10 to the minus 34th joule seconds. So unless you're really small like that, you're going to be over in here. So let's go and search for the relativistic quantum equation. And actually, Schrödinger did something that we're going to be doing now first, all right? And that's going to be arriving at the Klein-Gordon equation. So here we go to our special triangle in relativity, where we have mc squared, a right angle, and we have the PC, and then we have E for the energy. So then the energy squared is m squared c to the fourth plus p squared c squared. Now remember our prescription. Energy goes to an operator, IH bar, partial with respect to time, and the momentum goes to minus IH bar, the gradient, or the del operator. And here, you can write this. Some people like to write it as H bar over I with the plus sign. All right, preference as subjective choice there. So then when we use the kinetic energy plus the potential energy like this equals the total energy, and use these prescriptions here, that you're going to get the Schrödinger equation, all right? In other words, here, to get the p squared, for example, you would, you would square the h bar, you would square this, that's going to get you the minus, and then you would have this operator operating twice. So when that goes in there, you're going to have minus h bar squared over 2m, and this is a review, but we'll find this review important for the Dirac equation. All right, here we got this, IH bar, and then the derivative with respect to time. So that's the Schrödinger equation in 3 dimensions. And that's the one you would put in here for the F equals ma of quantum mechanics. That's the F equals ma of quantum mechanics. So what we want to do is the same prescription, starting not with the non-relativistic energy equation, but with this equation. This is the relativistic energy equation coming from our special triangle in relativity, special relativity. So that's relativistic. So if we do that, then we'll have for the E, IH bar, the partial with respect to T. And since you're going to square it, you know, that means we're going to apply it twice, like this. Apply it twice. You really don't need that parentheses there. I'm going to take that out. Don't really need that there. All right. If you want, you can just put a parentheses on the other side if you don't want to erase your notes. Okay, so then if you look at the right-hand side, the right-hand side is, well, it'd be equal sign here, because now we got the equal sign. And then now you have m squared c to the fourth, and there isn't anything there. So you just put the psi there. And then for this next one, what we'll do is we'll look at, say, if we take this, square it, we'll have h bar over I squared. All right, that's using this one here in there. And then when you apply this twice, you know, whenever you have a vector and they put a square there, that just means take like the dot product, you know, apply it twice. So that would mean here you have del dot del, and there is a c squared here we need to put in, and then the sign. Now, when we do that, you see these two i's are going to give you a -1. So you're going to have a minus h bar squared over here. And then you'll have the second derivative with respect to time. And then m squared c to the fourth on the psi. And then here minus, because the I is squared, h bar squared, c squared. And I get excited when I see equations like this because it has the h bar or the h and the c in it together. So whenever you have the h and the c together, see, indication that, hey, we're up in here, man, look at that. So this equation here is a relativistic equation. And you have your c and your h appear. Now, a lot of times in grad school, they'll let c equal 1, pick the units where c equals 1 and h bar equals 1. That makes things go away. I don't like that. I like to keep the h's and the c's in the equation. Okay, so if we were to, let's say, divide by h bar squared c squared, then you would have over here a -1 over c squared. Let's go ahead and do that. So you divide by h bar squared c squared, you get 1 over c squared here. And that's equal to m squared. Now, if I divide by c squared, the c to the fourth drops down to c squared. And if I divide by the h squared, I'm going to get h squared down there. And then this will be minus the Laplacian. Okay, now I can bring this on the left-hand side and have this cool equation minus, and see how the c with the t there, isn't that nice? Relativity. And the right-hand side is m squared c squared over h bar squared psi. And remember, like in one dimension, you would have this. So here you can see this is quite similar to our wave equation. Remember our wave equation, classical wave equation, we had this equals 1 over c squared. Now watch this trick. If we subtract like this, we get 0. And you might recall we said that the rest mass for light is 0. Because for light, when you have your angle here runs up to 90 degrees, where it's all momentum, because this is like your speed. If you don't move at all, then your p is 0, momentum 0, you're down there. And then if you're going at the speed of light, the E is all PC, and then we said that the M, the rest mass of light, is 0. Now that's the rest mass, because sometimes in our course and other places, what they'll do is they'll say, when you say E equals MC squared, they'll say this is an effective mass of the light. But the rest mass, see, light's not at rest, so that would be 0. So this equation, you can imagine, applies to light. Get the regular wave equation where the m is equal to 0. And once again, notice how the space and time appear on equal footing with the c with the t and the minus sign when you're squaring these. Isn't that very, very nice? Now, this equation was used first by Schrödinger, but doesn't give the energy spectrum for a hydrogen. So he then tried the other one, and the other one worked, the non-relativistic one. So here, there's a cute symbol, the box symbol, which is defined as 1 over c squared, the second derivative with respect to t, minus del squared, or the Laplacian. And that's called the D'Alembert, or the D'Alembert operator. You will see this sometimes. Sometimes this is written as the box with the little 2 there, like superscript. So that means if you look at this thing, if you bring here these things on the right-hand side, then you would have 0 on the left-hand side. You'd have 1 over c squared, the second derivative with respect to time. Then you would have minus the Laplacian working on this. And then you would have the mass term. But see, then all this is the D'Alembertian working on that. So you could have this cool equation, the D'Alembertian, plus m squared c squared over h bar squared. Isn't that nice? You have relativity constant, you have the quantum mechanics constant, and then you have the mass of the particle. You have this equal to 0. That's a very cool way to write the Klein-Gordon equation. And the Klein-Gordon equation does have application where you have a particle, say, that has a spin 0, and other applications, or you can see here when the mass was 0, for example, we got the classical wave equation. Then you might want to say, well, how do I incorporate the potential energy in here? And we're not going to pursue this. We're going to go to the Dirac equation. But what you would do is when the energy got replaced by this derivative and the momentum got replaced by here, you would add, say, the potential energy. But now I'm going to emphasize that this would be potential energy for space, and then you could add here potential energy for like time. So the potential function becomes a 4, like a 4 vector. It has like 4 components, and then it can be a function of x, y, z, and t. So this is called a scalar potential, this one here. And it actually becomes part of the vector, 4 vector. L3, the Dirac equation. Paul Adrian Dirac. There he is. This is marvelous, this theoretical physics that you're going to see shortly. Just marvelous. Well, let's go back to our triangle where we said that the E squared is equal to m squared c to the 4th plus the p squared c squared, which I think is easy to remember because if you put here mc squared and then remember to put pc here, you're all set. Then when you do the Pythagorean theorem, you have e squared is m squared c to the 4th plus p squared c squared. Now, what Dirac is going to do is consider a derivative, that's a single derivative. He's going to consider a first-order differential equation. Now, this is a very strange idea, because then you're saying that the energy is the square root, and I'm going to go ahead and put this one first, p squared c squared plus m squared c to the fourth. So if you do this, and then you're going to let E go to be I h bar, partial derivative, and you're going to let P go, and we can use the minus sign. We don't have to do h bar over I, we just do this one. Then when you get the squared here, see, that's going to be, when you square that, it'll still be minus. You'll have an h bar squared. Then you'll have the Laplacian, like we did for the Schrodinger equation. But see, now when this goes in there, so you take the square root of like derivatives, like what? Like, what is that? So here you would have I h bar, partial derivative with respect to time. And here there is a c squared in both places. So let's pull out one of the c's. We pull out a c. Then we'll have here, this will be a minus h bar squared, and then the del squared, plus m squared and then c squared. So if you put the c back in, you have minus h bar squared, c squared, and del squared, and that's what you would, if you put that c squared in there, it comes in as a c squared basically, and then if it comes in here as c squared, you get c to the fourth. This is almost like taking a square root of a differential equation. I mean, well, it's like a differential operator. You're taking a square root of a differential operator. And how are you going to do that? Now, most people would stop at this point and say, this is nonsense. But when great discoveries are made, you have to consider what others would consider to be nonsense. Let's look at this. Let's look at this here as without the derivatives just for now. Let's go ahead and put the square root. You got p squared, c squared, plus m squared c to the fourth. So just look at this here. That's what we have here, but let's look at this. How can you even take a square root of this thing? Well, Dirac says if you took a square root, you wouldn't have the squares then. So here, you pull out the c squared, there'll be a c there, and then you'd have some, say, so here we're going to pull out the c first. So we do that, then we'll have p squared plus m squared c squared. So if you do that, you'd have some alpha 1, say px, plus some alpha 2, py, plus some alpha 3, pz, plus some beta in front of the m squared. Well, that would be mc. That would be mc, because you want the, you're taking here the, you're having the first power. So let's look at this. If you take this thing and square it, then you would in principle get this, but this is nowhere like regular algebra, because if you do that, if you're gonna do this thing the regular way by just squaring that thing, if you want to square that thing, then you're gonna have something like, this will show up, but then you'll have stuff like this, cross terms, and you get two of those, say px and py. But since there's no cross term here, that would mean alpha 1 or alpha 2 would be 0, but then when you have the other cross terms, you're basically going to find that the alphas are all 0, but then you can't get the px squared because they're all 0. In other words, this is like not making any sense, all right, that if you do this, because all the cross terms are gone, and the cross terms, another cross term would be, say, alpha 2, alpha 3, and that's py, pz, like there isn't any of those in there. So that means one of those have to be 0. But if you already pick alpha 1 to be 0, then now alpha 2 has to be 0, or alpha 3 has to be 0, and you're going to get nowhere. Dirac says, let's do it anyway. All right? So in other words, p squared c squared plus m squared c to the fourth, that must equal c squared alpha 1 px plus alpha 2 py plus alpha 3 pz plus beta mc times, well, you're squaring it, so you have to multiply it by itself, all right, because we're squaring this thing, right? We square the left-hand side, you take the square root away, you square the right-hand side, you write this down twice. Now, Dirac says here, we're going to demand to get over here, we're supposed to get px squared plus py squared plus pz squared times c squared, and then plus m squared c to the fourth. So what Dirac is saying, if you take these two, alpha 1 squared will have to equal alpha 2 squared, alpha 3 squared, beta squared, and it has to equal 1. All right? Because c, then m squared c squared, then you'll hit it with the c squared there to get c to the fourth. It has a 1 there, so that means the beta squared is 1. But also, here, if the j does not equal to k, then the alpha j, alpha k, plus, in other words, here we're going to take one of these, say 1 with 2, and then 2 with 1. So we're going to look at one, say alpha 1, alpha 2, plus alpha 2, alpha 1. And since there's no px, py term, that has to be 0. So what he's saying is if that the j's and the k's are not equal, then this has to equal 0. In other words, these have to anti-commute. And same goes with the alpha j and the beta. Now, most people would say, how can you get this? But see, Dirac, matrices can behave this way. So I can get this to work if these alphas are not regular numbers, because there's no way it's going to work at regular numbers. Everything would want to be 0 or something, a contradiction. But if it's a matrix, there are matrices, we can make this work. So here's the genius. Dirac interprets these equations as matrix equations. So therefore, the AJ with the, or alpha J with the alpha K like this, if they're both the same, then you get 2 of them. And you want 1, so that's going to be an identity matrix. And then the delta JK, so when they're not the same, you get the zeros. So that needs to be the case. And then here, if you look at the alphas with the beta, anti-commutator has to be 0. And then if you take the beta squared, you need to get 1, or the identity matrix. But when we look at Pauli, the Pauli matrices, we find that we get sigma j with sigma k anti-commutator is 2 times I delta jk. They anti-commute. Now these are 2 by 2s. We have 2 by 2s, we have these, remember we have those. Say 1 is this one, the x one, and then we had the y one, then we had the z one, and then we have the identity matrix. But the problem is, see, these alphas have to anti-commute with beta. Now that won't work here, because if you took one of these things, and you know what's left, beta would have to be I. Well, see, beta squared is I, but see, if beta is I, then if you put I there, you would get the same thing back. And if you put it on the other side, you would get the same thing back. And then if you add them together, you're not going to get 0. You're going to get like 2 of them if you add. So that's not good. But then Dirac would reason, or we're going to reason along like Dirac, why 2 by 2? Aren't we in a 4-dimensional world with x, y, z, and t? So wouldn't we expect a 4 by 4? We try 4 by 4 and then use Pauli as our guide. So here, Pauli as a guide, we're going to have the 1s go along this diagonal. Say this diagonal like that. And you could think of this as what we did is, if we're thinking, break this up into 2 by 2s, we're putting the big 0 matrix there, and we're putting here Pauli 1 there and Pauli 1 there. So that's kind of what we did there. We can summarize this in that fashion. If we do that, then the second one should be, put 2 there, like that. And then that would get you here. So I'm using this guide. I'm using this as the guide. This is the guide. Then I would have 0, 0, 0, 0 up in there. And then I would have a 0 minus I, 0. Then I would have a 0 minus I, 0. And then I would have the 0, 0, 0 like that. Then if I did the third one, using the guide again, like this, say with the third case, 0, 0, 0, 0, then I would have 1, 0, 0, minus 1, 1, 0, 0, minus 1. Then what remains is the beta one. And when you're doing theoretical work, you play around, so all this is not obvious. In fact, most people would have not even gone this far, they would have given up. But to find things, and what Dirac's going to find here is that what'll work for beta is to put the identity here and negative the identity there, and this is going to work. 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, then minus 1, minus 1. Now, when you play around like this and do something like this, you really have to check it out. You gotta like do it to make sure that it's gonna work out that way. So let's check a couple of these. Let's check alpha 1 squared. and make sure we get the identity. So that would be 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and this is 1, 0, 0, 0. We put it down again, 0, 0, 0, 1. All right. Isn't physics wonderful with all the variety? Mathematics. So now if we do the matrix multiplication, we take this, turn it sideways here, and we pick up that 1. We turn this sideways here, we get 0. We turn that sideways there, you get 0. You turn that sideways there, you get 0. You turn this sideways here, you get 0. You turn this sideways there, you pick up the 1. You turn this sideways there, 0 and 0. This one sideways, 0. This one sideways, 0. This one, whoops, we pick up the 1 there, say it's the second one. And you get that. Here, 0, 0, 0. The last one's going to get you to 1. It works. Now, there's a shortcut way in doing this. You could say that this is like taking the 0 matrix with the Pauli 1 and 0, and I'm going to multiply here matrices rather than the individual components. If I do this, I would get, up in here, I would get sigma 1 squared. Over here, I would get 0. Here, I would get 0. And here, I would get sigma 1 squared. But if you take the Pauli matrix, the sigma 1, well, we already have done this. I'll do it again. Then take that sideways 1, take that sideways 0. Yeah, you get the identity. So you get the identity here, there, and there. And that would mean you have this. All right? So that works. Do they anti-commute? Well, if you looked at, say, one of these and added one of those, you can do the shortcut, with the Pauli in place. So this 0 really represents 0, 0, 0, 0. See, we're doing this kind of thing. And then here, if you have the second one like that, it's fun to do the math 4x4 too, so you can do either way. And then we switch these like that. So when we look at this thing, we're going to get sideways, we'll have the 1 and the 2. And you got to keep the order. And this sideways gets you 0. This sideways gets you 0. And this sideways gets you the 1 and the 2. And then over here, if you go sideways, you get the 2 and the 1. You go sideways there, you get zip. You get zip. And you get the 2 and you get the 1. So that means up in here you have the anti-commutator. Down in here, you're going to have the anti-commutator. And since the Pauli's anti-commute, you get, if you wanted to write it out, you would have a 4x4 with all zeros. You get 0. So you can check out some of the others. And I recommend doing it both ways for some of them. Doing it by the 4x4 and then doing it by the Pauli, shortcut, where you're looking at chunks of 2x2s. L4, spin, and antimatter. In anticipation for this, I'm showing you Dirac and antimatter. Now, what is antimatter? Well, antimatter is, they discovered that the electron has a sister particle, the positron, and we're going to see that it's going to come out of the Dirac equation. And that if these two should meet up, they annihilate each other and you get pure energy. You get 2 photons because they come together. Then the conservation of momentum says that when the photons go out, they have to go out in opposite directions so that the momentum's conserved. So let's see if we can get this and the spin also. We come back here for the Dirac equation, and we can write this as C times the alpha vector dot the momentum vector plus beta mc. And then remember that this came from the square root of p squared c squared plus m squared c to the fourth. And that's the energy. So when we hit that on here, then we get the energy. So the Dirac equation is going to be C, and you could put in, those derivatives for the P if you want with that prescription, but I'd rather not. I can get a lot done without doing that. In other words, without doing this. This goes to minus I h bar, the del operator, and the E, goes to I h bar, the partial with respect to t. But for now, I want to leave it this way. So this is plus, down in here, we're copying this, beta mc, and that's going to operate on, wave function, and that's going to equal E times wave function. And what I like to do is solve for the particle at rest, the simplest case. If the particle is at rest, this is nice because then this momentum is zero. So that means we have a simplified equation, beta mc squared on the psi is equal to the energy. And it kind of makes sense there that the energy is mc squared at rest. You're at rest. Let's solve this thing. And we'll get a lot of richness out of this very simple case. Now remember what your beta is. I'm going to put here mc squared, and then I'm going to put down the beta. Remember the beta had identity 2 by 2 in the upper left, and then the identity with the negative sign down there. And it's important to check, that did work. Maybe wouldn't be a bad idea probably just to check one of those ourselves. In other words, if you had an alpha 1 and you had beta, and plus the beta alpha 1, would that give you the 0? Okay, so let's do it using our shortcut. This is sigma 1, and 0. And this is identity, and this is minus identity. And then we're going to add here identity minus identity with the sigma 1s on the right side. So this would get you sideways here is 0. Sideways there is going to be minus sigma 1 because the identity doesn't change it and there's a minus sign. Sideways there we'll get sigma 1 because identity times sigma 1 is sigma 1. Sideways there gets you 0. When you go in here, sideways there gets you 0. Sideways here gets you a sigma 1. Sideways here gets you a negative sigma 1. Sideways there gets you 0. And if you add these together, you can see you are going to get 0. So that's important to have confidence that this beta is what it is. All right. And that'll work. See, that'll work no matter what that. In fact, you could say here, let's do it with the J case, all three of them, and let's make that J, 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 and J, 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 J. I just showed it's true for all three of them. And if you take beta squared, where you have the I, 0, and the minus I like that, have the I, 0, 0 minus I. If you do that, Sideways here gets you I squared. Sideways there gets you 0. Sideways here gets you 0. Sideways there, negatives cancel, I squared. And if you square the identity 2 by 2, remember, that's a 2 by 2, and that's the identity. That's going to simply give you the identity. And when you do that, you're getting 1, which represents, if you want to write it out as a 4 by 4, it has all the 1s along the diagonal. So that's important to have confidence that this is the beta. This will work. So, because earlier I just did that without really justifying it. Now we have just proven it. So this is going to equal here, working on psi. And now here you have the identity. When you don't have a matrix, it's assumed that you have the identity matrix like this. And this is an eigenvalue problem. Oh, energy. So this is the eigenvalue problem where the energy is mc squared, but I have here 4 solutions because I have a 4 by 4 matrix. So the solutions are for the eigenvectors. Let's just say this is proportional to, don't worry about anything else here, just want to essentially find the vectors. And here, this would be 1, 0, 0, 0. So you have an eigenvalue problem solved when you're diagonalized. Let's look at that here and prove that right here. For example, if you were to take this one here, with the mc squared, and multiply by this thing, you would get here mc squared. Take this thing sideways, there you get a 1. Take this thing sideways, there you get a 0. Take that thing sideways, there you get a 0 and a 0. So see, you get the same thing back. You get the same thing back. So if we take, for the next one, we have 2 states where the energy is mc squared. Look at that, spin up and spin down. Then we have 2 more solutions, that's the antimatter with the negative cases. So if we take this third one, and then we take here for the 4th one, we have 4 solutions. So you could say 2 had E mc squared, and then you could say, you know, this is, looking at the top part, it's a spin up and spin down. And then this one, looking at the bottom part, it's a spin up and a spin down with the negative energy. Now, the positron was discovered. In other words, this is your electron, this is your positron. One problem though is the positron does not have negative energy, but it has the opposite charge of the electron. And Dirac could have predicted this because, see, Dirac is doing this in 1928, and this is discovered in 1932. But Dirac didn't interpret this in that way. He brought protons in and things got a little bit messy there. And this gets corrected with quantum field theory, where this is just the beginning of the relativistic quantum realm. But what we are seeing here, that by the marriage of relativity and the quantum world, where the Dirac equation is dealing here, you know, with the H bar and with the C, that the children that are born here, you get spin up and down, and you get another pair, another state. So this is the matter and this is the antimatter. So very, very elegant theoretical physics, just super. and one of my favorite classes to see the Dirac equation. And this is usually taught in graduate school. I never saw the Dirac equation as an undergraduate, but you see it here in this course. And we see spin and antimatter. The spin of the electron come out naturally. It comes out naturally, spin up and spin down. When my daughter Frances was taking high school chemistry and she was learning about spin and going crazy, and she asked me, I says, don't worry about it. I says, you're not going to understand it any better than what your teacher's teaching you unless you become a physics major or take advanced physics and study Dirac, where you can then see where the two cases that are going to come out, there's up and there's down, and that's coming from the spinors, and the spinors come from the Dirac equation. So she was happy with that. Well, she wasn't really happy, but she was happy that she didn't feel that it was her fault that she didn't understand what was going on with the electrons. And you then fill up energy levels. Like here, I remember the old 2p or something had like 3, and then you could start filling them up like this. Now spin down, and then now we're all filled up in the 2p orbital or something. All right, so we are finished with the Dirac equation. I hope you enjoyed this profound discovery and the genius of Dirac to come up with this kind of a solution to a problem.